let's see. We didn't meet Tuesday because there was another hurricane. I can't even remember its name anymore. Sally, yeah. It was very boring. I was very unimpressed.
It was kind of like, so when we had Barry a few years ago, my dad called it Hurricane Barely.
That's pretty clever. I guess to keep everyone up to speed with what's going on, I sent out an email saying that the unit test 1, you can take it anytime today. So it's open, it's ready to go. You can take it today, anytime up until tomorrow by 6:20 p.m. So you can take it by tomorrow by 6:20. It's 100 minutes, and yeah, that's pretty much all I got. It's like 20 something questions. 2/3 of them are quick answer, and then there's like 6 or 7 that are a little bit more engaged. So besides for that, yeah, so you can take that test here. It's the second link in Moodle, so everyone should see that. So other than that, I will not be talking about the test today, and instead we will be moving on to law of sines and perhaps even law of cosines. So I was going to do this cool little proof to show how, well, actually, let me back up a little bit. And did I start recording? Yes, I did. Okay, cool. So we've been dealing with right triangles. Right triangles allowed us to view very specific properties involving trig functions. So, you know, we triangulate, we get this triangle, we figure out opposite, adjacent, and hypotenuse, all of that fun stuff. But what about if we don't have a right triangle? What about if we have an oblique triangle? So an acute or an obtuse triangle, and we want to figure out information about the sides or the angles. So again, I was going to do this neat little proof about it. And if you're interested in that, you can just ask me some other time, because the hurricane keeps taking all of my class time. So I'm not going to talk about it in class. So we're just going to assume its validity. See, I had this awesome little proof and everything, and now it's going to go to waste. So we're just going to start off with the formula itself, the law of sines. So this is for any triangle. This doesn't have to be a right triangle. We are now generalizing from a right triangle to any triangle. So in any triangle, the law of sines states that, well, it's these ratios. It's this equivalence between ratios. And in other words, you can solve any non-right triangle. So you can solve any non-right triangle if you know 2 angles and a side, or 2 sides and an angle, provided one of those are corresponding. So in other words, you need to know a corresponding angle and side, such as you need to know the angle A and its corresponding side, or the angle B and its corresponding side. We'll see some examples. It'll make more sense with examples. So with that being said, we're going to, well, let's utilize the formula here, and given all this information, we're going to find little b. So if we were to draw this out, we would definitely see that this is not a right triangle. Let's see, 150, that's an obtuse triangle. You don't have to draw it out. This is just to help us. So the obtuse angle would be 115. We can call that B. C, we can make this one 32. That means lowercase c would have to be down here. And we are looking for lowercase b. So notice how I'm putting those across from their corresponding angle values. So the letters do matter here in terms of positioning. We have to put capital B and lowercase b across from one another, and same with C's. So that, I guess, those variable usages tell us the positioning of everything. And so we're looking for lowercase b here. And so what the formula tells us, how we apply the formula is, well, this might be similar to, well, when we did similar triangles. So what's a ratio that we know among this formula? What's a ratio that we know? It's the C's. We have a completed ratio. Because we know little c, so we know little c and we know big C. So we know both of these. So if anything, this is a good ratio to utilize. And now we need to figure out which ratio do we pick to help solve the thing we're looking for. Of course, that's the B's, because we don't know what B is. We know capital B. So we can utilize the formula as such. So notice I'm not even touching the A stuff. We don't need it. We just don't even need it. So this is how you would interpret the formula. You need a completed ratio, and you need to use the ratio that helps extract the unknown value. So now let's go ahead and plug some values into these. Let's plug in what we know. So little c is 6.1 divided by sine of capital C, which is 32 degrees. That is equal to lowercase b, which is unknown, and sine of capital B, which is 115 degrees. And so finally, all we have to do is solve for lowercase b. Oops. So, depending on how well you know your algebra, you can either cross multiply, or you can just multiply both sides by sine of 115. In either case, you would get this. It's just one algebraic step. It might be one or two, depending on if you cross multiply or if you just multiply by sine of 115 degrees. But in any case, you get a bunch of calculator work here. So lowercase b, we legitimately just throw all of this in the calculator. And let's round it 2 decimal places. It doesn't matter. That sounds good enough. 10.43, and I guess this is yards, because we are finding a line segment. That would be it. That's lowercase b. So this is an application of the law of sines. Does anyone have any questions about this so far? If not, we're going to do another example pretty similar. Okay, cool. So let's go ahead and move on to example 2. We're going to solve for y in the picture, and I guess even more so, I'm going to just continue this problem and we're going to solve the triangle. Remember, solve the triangle means determine all the angles and all the sides. So we're just going to take it one step further as well. Let's start off by solving for y, though. So if we solve for y, y is right here. So we're going to use the law of sines. So remember, the law of sines states the equality of the ratios up here. So how do we utilize that here? I don't see A's, B's, or C's. Well, we have to figure it out. So we have to mix and match ourselves. If anything, to use the law of sines, we need a completed ratio. So if anything, do we have a completed ratio? What is the completed ratio?
Little letter over sign and a degree.
I mean, I don't know what you said, so I'm just going to fill in the blank here. We do have a completed ratio. And so when I say that, what I mean is we have, let me do this in a different color. We have an angle and its corresponding side. That would, I think that's why the picture here helps. We have a completed angle and side correspondence. And notice they are across from each other. They are across. That's how we know that these correspond to one another. 6 is a side that corresponds to 43 degrees. So the ratio there would be, well, our formula, we'll go ahead and put the segment first. So it would be 6 divided by sine of 43 degrees. So that's how we put this information together. So that is a completed ratio. If we have a completed ratio and an additional angle or side, then we can utilize the law of sines. So what are we looking for? We're looking for y over here. So if anything, we're looking for the segment y. And what is the angle that corresponds to y?
57.
Yeah, it's right there. It's directly across. So that's what would tell you that the angle of 57 degrees corresponds to y. That's what I'm going to use, that terminology throughout these next few sections. It's probably worth mentioning as well. This is 7.1 in the book. That'll probably be helpful. This is 7.1 in the book. We're going to skip around moving forward. This is 7.1 in the book. So let it be known.
No, for point two, 3.1. Okay, it was completely different.
I was 100% here.
Yeah, I'm surprised. Oh my, yeah. Radian measure.
Yeah, I don't you've been getting me now.
Radian measure, yeah.
No correlation.
Yeah, maybe I should have just started signing parameterization problems. So I think that's worth knowing. And so since we know y, the side of y corresponds to the angle of 57 degrees, then we can complete the law of sines formula like this. And this is how we use the law of sines. Once you set it up, the algebra is really helpful, or really straightforward rather. All you have to do is multiply sine of 57 to the other side. And then it's calculator work. So again, the algebra is not that bad. It's just, now we have to plug it into the calculator. I'll round it to 2 decimal places. I didn't specify here, so it really doesn't matter. And there's no unit, there's no yards, centimeters, anything, so 7.38 is fine. So that would be y. But as I mentioned, we're going to take this a step further. We're just going to go ahead and solve for the triangle, which means let's figure out the missing, anything else that's missing from this triangle. So if anything, we determined that y is 7.38. Let's see, what else are we missing here? Well, seem to be missing this angle. And we seem to be missing this side. What's that?
And they correspond.
And they correspond. So if anything, we cannot use the law of sines yet. Because,
On either the side length or the angle.
yeah, we need one of them to find the other. So we cannot, if we started trying to use the law of sines, so if I called that one little x, this would be big X, but the ratio would just be little x over sine of big X. That's multivariable. We are not in calculus 3, so we do not worry about that. So we have to figure out one of these values here. And I think one of them is much easier to figure out than the other.
The angle, we could subtract
180 minus.
Yeah, the angle. So we can figure out the angle really quickly. When you have two angles, the third angle is really easy to find. So that capital X, actually I might need this room down here. So let me write this up here. We know 180 is what all the angles add to. We subtract off 43 degrees, and then we subtract off 57 degrees. Cool. 80 degrees. And now we can use the law of sines, because now we have an angle and its corresponding side. And we need to compare that to a completed ratio. Now we have two completed ratios. I'm going to pick the one that's got less approximated numbers. So I'll pick the 43 and the 6. Because we need some sort of completed ratio. And if you ask, can I use the Pythagorean theorem? No, you cannot use the Pythagorean theorem.
It's not a right triangle.
It's not a right triangle, exactly. You cannot use, I've seen that before. So you would think it flows reasonably, but the Pythagorean theorem does not work unless you have a right triangle. And in fact, in the next section, we actually generalize the Pythagorean theorem. I think that's kind of interesting. So let's see, we know the angle. So we know that down here it's going to be sine of 80 degrees, and the numerator is going to be little x. So 6 sine 80 degrees divided by sine. Did any of you already figure it out?
It's 8.66.
8.66. How does that sound to everyone else? Because we got to make sure you're not lying to us. You would never do that. You're right. All right, cool. All right, so that solves the triangle. We know all the angles and all the sides. So in your homework questions, there will be quite a few problems. Well, quite a few being out of 5 questions here, I think 3 or 4 of them will have you solve a triangle, and you figure out all the sides and all the angles. Now there's something interesting here. Well, I guess before I start moving on, does anyone have any questions?
So for law of sine, you just use sine.
Yeah.
Okay. Don't use the cosine tangent.
Nah. How's that sound? Law of sines, you use sines. Law of cosines, you do something else. Want to guess what trig function you use for law of cosines? That's right, hyperbolic cosine. Just kidding. All right, cool. So bad jokes aside, let's move on to, so this was a situation we had when we had 2 angles. One's actually 2 angles and one side, and we were looking for another side. What about if we utilize the law of sines to find an angle? So we found sides so far, and every time we found an angle, we had 2 other angles. So what about if we are only given one angle and a bunch of sides, and they want us to find an angle? I mean, if anything, we can't use 180 minus the 2 other angles because we don't have 2 other angles. So we're going to use the law of sines to find an angle, which might be one step further than what we had before. So, if anything, to use the law of sines, we need a completed ratio. So, we need a completed ratio. That ratio, does anyone happen to see it
It's
without a diagram?
23.1 and 14.
Yeah, this is the completed ratio. That's why they use that notation of little a and big A. It makes it clear that that is the corresponding angle and side. So that's why they use that notation. Sometimes, in fact, one of your homework questions, I think this is a good time to interject this. Let's see, 7-1. Where's it at? Which one is it? Number 21. I remember getting questions about this notation. When they say AC is equal to 132 feet, they say it like that. This is little b. It's the same thing. The reason why is if you draw some triangle, there's A, there's B, and there's C. AC is referring to the segment here. But guess what that segment's across from? B. So that's what it means. So no more mystery. Cool. So that's the thing to keep in mind. And that'll tell you if you're in the right, in the right section in your book as well. So if anything, we do have, as I mentioned, a completed ratio. So what do we set that equal to?
Big B over solid.
Want to help them out?
Would you use the 14?
What's that?
Would you use the 14?
Why 14?
Do you have it?
Blake?
So we're looking for angle B. Well, you're looking for the opposite, and there is no hypotenuse. So,
Logan?
And yes, 21 over sine of big B.
Yes. 21 over sine of large B. The reason why we're looking for big B, in order to have a ratio with big B, we need to have little b.
yeah, I think we all just overthought that a little too much.
14 because you have it. What a disgrace. But yeah, we use big B and little b. So notice C here is not even used. It's just extra information.
Trying to throw us off.
Well, I mean, that's just, at least it isn't my math lab. So now that we have this, we can go ahead. So really, I was trying to figure out how to explain this, because there's one of two ways you could think about this. You can cross multiply, or you can reciprocate both sides. Does any way sound more enticing?
Reciprocation.
Reciprocation. So the reciprocation way means if you have fractions on both sides, then you can just flip them. It's the same thing. So the reason I'm saying to do this, so we're just flipping both sides. If you do it to one side, you can do it to the other. And the reason why is now, Yes, and now the variable, at least the variable expression is in the numerator
And it's gonna be by itself.
after we do one more thing.
Yeah, after we multiply times 21 with signs.
And we do one more thing. Because it wouldn't be b by
And then
itself.
you gotta do the sign.
Yeah, so if anything, getting sine of b by itself is just a matter of multiplying 21. Don't start punching this in the calculator just yet. So I had a few people last semester during the midterm who did problems like this, and they put all of that in the calculator, and that was their answer. They said, okay, that's b. That's not b. It's sine of b. That's different. We're trying to figure out b by itself. We don't want sine of b. Or else it would have just said find sine of b. But it doesn't say that. It says find b as a variable by itself. But there's this sign in the way. What do we do?
Divide both sides by sign.
No. No, not that. What do we do?
Would you take like you do the thing where you take the sign, like the reverse sign or the
Yes, the inverse sign. Remember that? So that's how you get a sign away from the variable. You do an inverse sign. So yeah, you do an inverse sign.
I couldn't think of inverse. I'm trying to think of the word.
Yeah, so we do sine inverse of all of this junk, just because it's all over here. So now we're really starting to become math people, looking at these incredibly complex, composed expressions. And so that is what you can either put in the calculator all at once, or you could put this part in the calculator and then take sine inverse of the answer. In any case, however you decide to do it, you should get whatever answer I'm about to get. So it might be worth just trying one and seeing if you can get what I'm going to get. Now you might think, all right, cool, we found B. Well, let's hang on to that. Let's as I mentioned, we're going to go ahead and solve this triangle. So that means we need to figure out all the sides and all the angles. Naturally, I might need a little bit more room to write on. So I am going to, let's not minimize this. There we go. Why is this happening? Just click. All right, let's try it again. Okay. The point I'm trying to allude towards is the law of sines will not find an obtuse angle. It seems like a weird stipulation. The law of sines will not find an obtuse angle. I'm saying that right now. I forgot about it last semester when I taught this class, and I was very embarrassed. So I'm not forgetting it this time. The law of sines will not produce an obtuse angle. And a way to see this if we were to solve for for this triangle. So if anything, we have that A is 23.1 degrees. We thought that we found B is equal to whatever I said it was.
36.05.
Oh, thank you. C is still unknown, capital C. Little a is 14, little b is 21, little c is 8. So this is what we found in the problem. So naturally, there's only one thing we have to solve for. So you might think, all right, we solve for capital C. And how would you solve for C normally? Well, I mean, the simplest way you would do it this way. And you would get 120.85 degrees. But there's a problem here. There's a problem that may not seem too intuitive why this is a clear contradiction. Because the largest number has to have the largest angle. That is not the case. Here, there's an issue because the largest angle belongs to the smallest segment. That cannot happen. So, in other words, largest angle
Because it's corresponding, that makes sense.
must correspond, exactly, it must correspond to, so largest angle must correspond to largest segment.
So would you just have to find C first and then subtract?
So you can either find C or you can utilize that B is a reference angle. Remember that? So it turns out, so by running into this issue, it turns out that B is in fact 180 degrees minus 36.05. Because sine is positive in quadrant 2. Or you could solve for C first and then solve for B.
It's like 142.95.
36.05. And then from here, we can determine C. So really, so normally in general, I do suggest that you solve for the smallest segment first. So really, what we did was we walked into a bit of a trap. Now, if you were to do this on a test, I wouldn't really penalize you too much because it is something that someone may, do and not even think about it. So instead, what I'm going to do is, where's it at? There it is. What I'm going to do is absolutely annoy everybody by redoing the problem in the correct way that you're supposed to do it. So by adding this stipulation, well, law of sines does not find obtuse angles. Therefore, find the angle of the smallest segment. Because there's no way there's going to be more than one obtuse angle in any given triangle. That means by picking any segment that's not the largest one, you guarantee that it is acute, which means you will not have to worry about this issue. So you would think, all right, well, I want to solve B, and you would do it in that fashion, but as we all saw, it does not work out that way. So
C wasn't extra information.
isn't it crazy how that goes all, well, that's not inception. I don't know the word for it. Comes full circle? I don't know. I feel like I already said that today. And the last thing, I want to be a stale as a math teacher. Math teachers are never stale. All right, so if anything, we can solve for little c or little a. You can really solve for either two. We just don't want to solve for the largest segment. We don't want to solve for the largest segment. So really, it's probably better to solve for, well, really, we don't have a choice here. Yeah, we're going to solve for, so we're going to find capital C, which is the angle. And if we're solving this thing, we'll have to figure it out anyways. So here, the completed ratio, that still stays the same. And since we're solving for C, little c is 8, and big C is unknown. You can flip both sides. You can solve for sine of C. And you can either throw that in the calculator and prepare to apply sine inverse to it. Or do this. All at once.
So like, I know we don't see all the steps like through the calculator, but does sine inverse just cancel the sine?
No. That's because the, well, I'm trying to think, because there's a property, you're falling for the freshman dream, as we call it, which kind of a math meme, so it's not really well received by normal people. And it's the idea that numbers can be taken in and out, scalars can be taken in and out for sine and sine inverse to be right next to each other. So what you're assuming is that the 8s can just be moved around freely for the sine and the sine inverse to correspond with each other directly. That's called linearity, or the homogeneity property of linearity, and we do not have that for sine inverse. So in less technical words, no, they do not cancel. And by throwing all that in the calculator, we get 12.96 because we did it a slightly different way, so we're off by 100th according to my calculator, which big deal. I'm grading it, so I don't really care. But notice we get the correct angle. And then by finding B, All of that was finding C. By finding B, that one's going to be easy now.
Yeah, you just,
You just subtract. So that's you do not have to worry about this if you're not using law of sines to find an angle. This only matters when you're using law of sines to find an angle, is when you have to worry about the stipulation. Because the law of sines, well, guess what? The law of sines does not find obtuse angles. It just doesn't do it. It makes sense because the output of sine inverse is only negative 90 to 90. So it does not exceed that, which means it does not exceed and go into obtuse angles. But in any case, we also solved the triangle just now. We found all the angles and they already gave us all the sides. So hopefully that was as fun for you all as it was for me. Does anyone have any questions up to this point? If not, we're going to look at something that's really much easier. So the area of a triangle, you might know or might remember the formula for it, 1/2 base times height. But, well, you might look at these formulas and think, well, that's not 1/2 base times height. And the reason why is you don't always know what the base is. You don't know what the height is. So what's a way of knowing if you're given different information about the triangle? So this is the area of a triangle. If you're given, so this is normally interpreted as side, angle, side. So two sides and an angle. So if you're given all of that information, you can determine the area of a triangle. So notice we don't need the height, we don't need the base, we just need two sides and an angle. And notice, for example 4, you give us two sides and an angle. Well, guess what? That's very convenient. The area is 1/2, the two sides. See, it doesn't even matter about the number of formulas. They all work the same exact way. So that's it. That's all you have to do for this. So this one's much easier. Call it 100.23 meters squared. This is area, after all. Okay, well, that's law of sines. That's really it, just doing all of that. This whole section is just having you practice the law of sines and then some area formula. So if nobody has any questions up to here so far, then the homework, I was trying to think about this in my office. Anything, go to the right section in the book, please. It's 7.1 in the book. Here's the homework problems. I think they're all pretty fair. And I gave some sort of clarity for 21. And depending on how far I get in section 3.2 is when I'll assign this homework due for. If I don't finish the next section, this will be due Tuesday. If I do, then both of them will be due Thursday. Let's see how I do. So law of cosines, as you would imagine, we're going to be looking at the cosine function. And we're still looking at trying to solve oblique triangles. We're still looking at that. So we're still looking at solving oblique triangles. Pretty much what the law of cosines does is it takes the place of triangles where we have insufficient information to use the law of sines. The law of sines doesn't work in every situation. For example, law of sines requires us to have a completed ratio. But what about if we don't have a completed ratio? So a triangle of that example, well, as you would imagine, would be any triangle in the section. But let's say you had a triangle of, you knew this angle, you knew that this was 7 and this was 8. So there's no completed ratios here. So law of sines wouldn't be able to help us. So what do we do? And so it's the law of cosines that will step in and give us some more cases for different types of information we're given for triangles. So the law of cosines, it's really got one of 3 equivalent forms. So if you're solving, so notice that A and A correspond to each other, B and B correspond, and C correspond, with the other 2 variables scattered about in this very particular fashion. So there's 2 new situations we have that the law of sines wouldn't have been able to answer, that the law of cosines steps in to do. So if you had a triangle and you knew all 3 of the sides, law of sines can't do that. You have to have an angle and a side pair. So all 3 sides, law of cosines works. Or the example I had written down a second ago, 2 sides and an angle that doesn't correspond to either side. So example 1 says what happens to the third formula if C is 90 degrees. So what is the third formula? Third formula, I'm just going to rewrite it. But it says now capital C is 90 degrees. Okay, well that's interesting. What's cosine of 90 degrees? What is cosine of 90 degrees? Does anyone happen to know? Yeah, that's right, it's 0. So if this is 0, well, that zeroes out all of this stuff. So what are you left with? Oh, that's interesting. What does that look like? That's the Pythagorean theorem.
It's because if it's 90, that means that it's a right triangle.
That's right. So the law of cosines is a natural generalization of the Pythagorean theorem. So how exciting. So now we pretty much have the Pythagorean theorem for general triangles. And this is it. One of these forms. It's all relative based off of nomenclature, but I digress. But that's kind of the interesting thing. The law of cosines is a generalization. So we'll start with example 2 to really see how to apply this. B is 31 degrees, A is 4 inches, and C is 8 inches. Find lowercase b. Now, luckily, there's no stipulations with the law of cosines. It will find, I'm just saying this in general, but law of cosines, you don't have an issue with it can't find obtuse angles. It doesn't have that issue. But in any case, we do have an angle, and we have 2 sides. We're going to find this lowercase side. So we need to figure out which one of these formulas to utilize. Well, if anything, I think it should be clear which one of these 3 formulas we should use. Probably the only one that actually has a capital B in it, because we have a capital B. So the the formula we're using, I'm just going to rewrite it. We're going to use that middle one because it's the only one that actually utilizes a capital B. So we don't know what lowercase b is, but we know all the other ones. So that's 4 squared plus 8 squared minus 2, 4, 8 cosine of 31 degrees. Now I'm going to stop right here. Okay, maybe it doesn't come up in this problem. I'll mention it in the next problem. There's an algebra rule that people love to break, and you definitely cannot do it here. It'll make more sense in the next problem. So in any case, all of this, that's all numbers. Guess where all that can go? That's right. So, I mean, you could put this in your calculator and then anticipate that you're going to take the square root of it almost immediately afterwards, because
It's 25.41 after you put all that in.
well, let me go ahead. Now, it really doesn't matter because this isn't my math lab, so I really am not going to care about incredibly close approximations. If it's kind of close, that's fine by me. One four, that's good enough. And then b is the square root. So hopefully you all remember that from algebra. That's going to be close to 5, I bet. 5.01, that's fine. Well, inches, just to be technical. So this would be an application of the law of cosines. Now, what about if I asked you to solve this triangle? What would you do? So let's think about that prospect for a second. So what numbers did we have here? Someone who has their notes, can you call out the numbers for me?
Big B equals 31 degrees, little a equals 4, and c equals 8. Little c equals
What did we just find for?
8. Little b is 5.01.
All right, so this is where we were at in the problem. What about if I asked you to solve the triangle? What would you do?
You would go to the law of sines.
Yes, you go to the law of sines. So then we can go ahead and find capital C.
You'd want to find A first, wouldn't you?
Yes, thanks for calling me out on that. Yes, you don't want to find C first because it's not the smaller segments. I picked the bigger one on purpose. So if this was a solve a triangle problem, so this is where this resorts back to the law of sines, because now we have a completed ratio. We now have a completed ratio. And here we have to pick one of these to solve for, but you have to pick the smaller one, or else you might run into that obtuse problem. So then the completed ratio would be 5.01 divided by sine of 31 degrees.
Equals 4 over sine.
That's right, 4 divided by sine of, which would be capital A, because 4 is lowercase a, so we're looking for capital A. And we are picking this one first, so we can definitely avoid an obtuse angle issue. And we can flip both of them. I mean, the formula works if all of these are flipped anyways, so. Then whatever the heck that is. Oh, 24.28 degrees. Blake, is that what you got? And then from here, it's pretty easy to figure out capital C. Just 180 minus the 2. So capital C would have been obtuse, which means that law of sines would not have really given us the correct result.
So basically, the law of cosines just fills in what you need for the law of sines.
Yeah, law of sines is much easier to use. You should only have to use the law of cosine once. And then from there, you can use the law of sines for everything else. Because the law of cosines will help you find.
What you need for the law.
Yeah, in fact, it would be impossible to find something missing and then still not have a completed ratio afterwards. You would, no matter what piece you fill in, you will end up finding something corresponding. It would be impossible otherwise. But you will get used to this idea of solving by, so this problem I just did, this is a very standard trig problem. Law of cosines, and then the law of sines, and then property of triangles. Just a trifecta. That's, at least for problems in this section, that should be fairly typical. I mean, there's still another circumstance we've yet to look at, but this is the extension of that problem. What section? Well, this homework, that's a good question as well. Where in the book do you find this? Nope. Nope, it's not 7.2. That's why it's a good question.
I went ahead and wrote it. 7.2.
It's 7.3 in the book.
So close, yeah.
7.3, because I think 7.2 is the ambiguous case of sines. Yeah, I don't really like that section. So this is 7.3 in the book for the law of cosines. Well, let's keep going. Let's see, we have 3 more problems left. So let's do those and call it a day. All right, so hopefully everyone okay. My goodness. There we go. So hopefully everyone has this already. And if not, here it is for if you go back in the video. So let's move on to example 3 here. So in this problem, well, this actually looks very familiar. We've had this problem already. We have done this problem already. We did this problem using law of sines, but now we're going to use law of cosines. Well, 1, because we're in a law of cosines section, but 2, because when we did this problem in the previous section, we had to find C first. So this was that problem that I worked out twice. So for this problem in the previous section, we had to find capital C first and then find capital B, because it ended up being the case that lowercase b was obtuse. And law of sines does not find obtuse angles. Law of cosines does not have such a stipulation. Law of cosines will find acute and obtuse. So in order to use this formula, we have to pick the correct formula. And it just so happens, well, it just so happens I have an arrow pointing right to it. The capital A is kind of just extra information. So we don't even have to use it. So I'm going to rewrite the formula. So it just so happens we're using the same formula as before, because that's the only one that utilizes capital B. So let's go ahead and plug in everything we know. So again, we're not even using capital A. So that's 21 squared is equal to 14 squared plus 8 squared minus 2 times 14 times 8 cosine of capital B. And here is where I will have an issue. It's something you may do. If you simplify this by putting all of these numbers here in the calculator, I'm not going to be very happy about that.
You can't separate the cosine.
It breaks order of operations. You cannot combine those numbers together that I just have underlined in red. It breaks order of operations because, well, the reason why is because these numbers are stuck to cosine. And until you get rid of cosine, those numbers cannot be added or subtracted to just rogue numbers out here. You cannot add those together. So what you can do instead, to not get that point, that automatic point deduction, well, if anything, let's go ahead and clean up some of the finer details. So 21 squared, so that's 441. 14 squared plus 8 squared, we can do that. So that's 260. And then minus, and we can do all of that. 2 times 14 times 8. So this is all okay. But what we have to do, so again, you cannot, and I know someone's going to do it. This is my warning. You cannot bring those numbers together. It breaks order of operations. That 224 is stuck with the cosine.
So it might help like putting parentheses around everything on that right side,
You can.
just so you know it's all together.
If whatever you need to do to tell yourself, don't fall for that thing that Brad told you not to fall for, then do it. But instead, you would subtract 260 on both sides. So that's 441 minus 260. 181 is equal to negative 224 cosine of B. Cosine of B is now negative 181 divided by 224. I am dividing. This is a division. And then B is, remember the name for it?
Inverse cosine.
Inverse cosine, that's right. So notice this does give us an obtuse angle, which is good. So law of cosines does not have the same stipulation about obtuse angles. And we know A, we know B. We can figure out C now. Let's go ahead and just solve it. Oops. $140.90 minus 23.1. It's equal to something. $13. Just 13. Cool. Does anyone have any questions about that? Okay. So, example 4, they give us 3 lengths. They want us to solve the triangle. So, we need to figure out 3 angles. So, there's no way we can use the law of sines for this because we have no completed ratios. We need at least one angle to use the law of sines. We don't have that, so we have to use the law of cosines. And what I would recommend, because we can solve for any angle we want. Really what I recommend is, I recommend solving for the largest. Because I know the law of cosines isn't going to steer me wrong. And if I have to use the law of sines next, then I don't want to use the wrong angle. So really, it's up for us to choose. Find angle of largest segment. Because I know this will not steer us wrong. We will get the right one. And if we have to use law of sines next, then we're just anticipating this. So we're finding capital B, which use the same exact formula. Oops. And let's go ahead and start plugging stuff in. Oops. Okay. There we go. So it's pretty much the same algebraic steps as before. I'm just doing it one step at a time. And ultimately, you would get that B is the inverse cosine, really 16 divided by 336. Because the negatives cancel when you divide by negative 336. So it helped us determine B, which it turns out we will not have an obtuse triangle because the largest angle we have is acute. But it doesn't really change anything. But now we figured out this angle. Now we have a completed ratio. And the reason why I'm corresponding 87.27 to 18 is because little b is 18. Capital B is the 87, so they correspond. So that is a completed ratio. And then we can use that to help us find whichever other angle we want. And this one, it really doesn't matter. So just pick A, doesn't matter. And I pick 14 because that's little a. And if you do all this correctly, because I'm running out of room and time, that's what I get. And then you can figure out the final angle pretty easily by subtracting. And for C, we get 41.75. Let me get through this, the area formula as well, because this one actually has no trig in it. It's just kind of there. They give this formula. And S, this thing S, is 1/2 of the sum of all the sides. So it wants us to figure out the area from the triangle from the previous problem. Remember, A was 14, B was 18, and C was 12. Just from the previous problem up here. So little s is 1/2 the sum of all of those. What is that? 7 plus 9 plus 6, 22, I guess. And then the area is square root 22, 22 minus 14, 22 minus 18, 22 minus whatever C was, 12. And once you have that down, you are good for the day. So I'm going to make both of those sections due a week from today. More importantly, make sure you do the test. You have until tomorrow to do the test. Please make sure you do that. If you have any questions, shoot me an email. Other than that, that's all I have for today. Good day.